Beneath our feet, the ground feels solid, but Earth's crust is always shifting, breaking and rebuilding. Over millions of years, continents drift, collide, and reshape the face of the planet. Today we'll uncover how this restless crust changes through time. If you enjoy the journey, please like, subscribe, and share. Thank you for watching. Now let's begin. The Earth forms more than 4 billion years ago from dust rock fragments and gases that orbit the young Sun. The heat from impacts, radioactive decay, and gravitational compression keeps the planet almost entirely molten. In this early stage, there is no solid crust as we know it today. The outer layer is a churning ocean of magma shifting and circulating under the influence of constant energy. Slowly as time passes and the outermost layers radiate heat into space, the surface begins to cool. The first thin, solid skin of rock starts to appear. This primitive crust is fragile, unstable, and easily broken by impacts from the leftover debris of planet formation. Every large asteroid or comet that strikes the surface melts patches of the crust, returning parts of it to liquid form. Still cooling continues, and over many millions of years, portions of the thin surface harden into more durable structures. This earliest crust is different from the continents we see today. It forms mainly from basalt, a dark, dense volcanic rock, created as molten material from the mantle reaches the surface and solidifies. The first crust is therefore more like the modern ocean floor than like the continents. Its thickness is limited, often no more than a few kilometers, and it floats upon the softer, hotter layer below known as the asthenosphere. This layer of partly molten rock acts as a support and allows the outer shell to shift and respond to internal forces. Yet in these first hundreds of millions of years, the crust is far from stable. Constant bombardment by meteors reshapes the surface again and again. Vast impact basins form, filling with melted rock, only to cool and solidify once more. The cooling of the surface is not uniform. Some areas lose heat faster, becoming more rigid, while others remain warmer for longer, making them weaker and prone to collapse. Over time, this uneven cooling encourages the formation of patches of crust that vary in thickness and stability. These patches drift and move slightly relative to each other, though the full system of plate tectonics does not yet operate in the same way as it does in later eons. Instead, the young crust behaves like rafts of solid material, floating upon a restless sea of molten rock. Water also begins to play a role. As the Earth cools, water vapor in the atmosphere condenses and falls as rain. Pools of liquid water accumulate on the surface, collecting in low areas, created by impacts and by crustal subsidence. The interaction of water with the crust alters minerals at the surface, leading to the first processes of chemical weathering. Water also helps to concentrate heat in some regions, as it seeps into fractures and promotes melting when it returns to depth. This connection between water and rock becomes a defining factor in the long evolution of the crust. Fragments of this earliest crust are almost entirely lost today, recycled into the mantle or destroyed by impacts. Yet tiny remnants survive, preserved as ancient crystals within younger rocks. One of the most famous examples is zircon, a very durable mineral that resists breakdown. Some zircons found in Western Australia date back more than 4 billion years, providing direct evidence that solid crust and liquid water already existed at that time. These small grains tell us that even in an environment of high heat and bombardment conditions allowed portions of the surface to stabilize. As the Earth's crust thickens in certain places, it becomes more resistant to destruction. Heat rising from the mantle continues to push upward, cracking and weakening thinner sections of crust while thicker and cooler portions endure. Over long spans of time, the crust experiences cycles of growth and loss. New basaltic crust forms from molten rock at the surface while older sections are disrupted, buried, or melted. Slowly the seeds of continental material begin to emerge, These are richer in silica and lighter in density than basalt, allowing them to float higher on the mantle. They represent the first steps toward the continents, though at this stage they remain small and scattered. The overall appearance of the planet during this time is stark and different from the present. The sky is filled with dust from frequent impacts. The atmosphere is thick with carbon dioxide, methane, and water vapor. The surface is broken by wide impact basins, lava flows, and small areas of rising crust. Steam vents and volcanic eruptions are constant. Oceans are limited but growing. The contrast between fragile stability and violent disturbance defines the early crust. In this setting, the principles that govern crustal change already begin to take shape. Heat flow drives movement. Density differences between rock types control which materials rise and which sink. The presence of water accelerates transformation. The crust is thin, unstable, and temporary, yet it lays the groundwork for later processes. Each cycle of melting and solidification adds new layers slightly more complex than the last. Each fragment that resists destruction becomes a building block for the continents to come. Even at this early stage, the crust demonstrates the balance between construction and destruction. Cooling favors the growth of solid rock while impacts and internal heat drive its loss. The crust never remains static. It is always being reshaped. This balance remains a defining theme throughout Earth's history. The crust is the outer shell of the planet, but it is never fixed. It changes in response to deeper forces and external events. What begins as a fragile skin of basalt eventually becomes a mosaic of ocean floors, continents, and mountain chains, but the principle of constant change is already present. As the first hundreds of millions of years pass, the Earth transitions from a world of molten seas to one with recognizable rock, water, and atmosphere. The earliest crust, though thin and unstable, represents the foundation of all later geological development. It is the starting point for the long story of Earth's surface, a story in which creation, destruction, and renewal repeat endlessly over deep time. As the Earth's crust matures beyond its earliest fragile stage, certain portions become more resilient than others. These fragments gradually evolve into what are called continental seeds, or protocontinents. They differ in composition from the denser, darker basaltic crust that makes up the oceanic floor. Instead, they are enriched in silica and lighter elements, giving them a lower density and allowing them to rise higher above the mantle. This buoyant quality helps them survive repeated cycles of melting, burial, and deformation. Over immense spans of time, these fragments accumulate into cratons, which are the stable ancient cores of today's continents. The formation of continental seeds begins with partial melting. When basaltic crust or the upper mantle partially melts, the resulting magma is not identical in composition to its source. Silica and lighter minerals concentrate in the melt, while denser minerals remain behind. When this silica-rich magma rises and solidifies, it creates lighter continental material such as granite. Each small patch of granite-rich rock is more resistant to being recycled back into the mantle. When many such patches merge and grow, they establish the first roots of continental crust. These roots are thicker and cooler than surrounding rock, which further stabilizes them against destruction. Evidence for these early seeds comes from ancient rock outcrops found on modern continents. Some of the oldest known rocks, more than 4 billion years old, are found in Canada, Greenland, and Western Australia. These rocks show that by this time portions of continental crust had already formed and persisted. Within them are ancient minerals like zircon crystals, which carry geochemical signatures pointing to repeated cycles of melting and differentiation. Such cycles indicate that the early Earth was not only creating crust, but also reworking it, producing more evolved and silica-rich compositions over time. The growth of continental seeds is not uniform across the globe. Some areas remain dominated by basaltic crust, while others develop thicker and more buoyant crustal blocks. Collisions between fragments driven by mantle forces help to amalgamate these blocks. Where pieces of protocontinents collide, they may partially melt at depth, generating more granitic material and thickening the crust further. In this way, each collision and reworking event adds to the survival chances of continental crust. With greater thickness, the roots of these blocks sink deeper into the mantle, a process that geologists call crustal keels. These keels provide extra stability, insulating the blocks against recycling. Water again plays an important role. The presence of water lowers the melting temperature of rocks, making it easier for partial melts to form. Subduction of wet basaltic crust introduces water into the mantle, fueling the creation of more silica-rich magmas. This recycling process is critical to the long-term growth of continents. Without water, the early crust might have remained more uniform, dominated by basalt, with fewer opportunities for lighter crust to form. With water, however, the pathways for differentiation and continental growth expand, accelerating the emergence of stable blocks. Over time, these small continental seeds develop into cratons. A craton is a large, ancient and stable piece of continental crust that has survived billions of years of tectonic activity. Cratons typically consist of two main parts: a shield where ancient rocks are exposed at the surface, and a platform where younger sediments cover the old basement. Shields in Canada, Brazil, Africa and Australia preserve the earlier surviving records of Earth's crust. The fact that these rocks remain intact today shows how resistant cratons are to destruction compared to other parts of the crust. The survival of continental seeds and cratons also shapes the surface of the planet. Because they are thicker and more buoyant, they stand higher than the surrounding oceanic crust, forming the first stable landmasses. These landmasses affect climate by altering wind and ocean circulation. They influence the chemistry of oceans as rivers carry weathered material into the seas. They even provide sheltered environments where life can eventually take root. Though still small and scattered, the emergence of continental seeds begins to transform the planet's surface, from one dominated by water and basalt to one that includes stable land. Geologists reconstruct these events using several lines of evidence. Ancient zircon crystals preserve isotopic data that reveal when crust was forming and reworking. The chemistry of ancient rock shows repeated cycles of differentiation, confirming that continental material was generated from basaltic sources. Structural studies of cratons demonstrate how thick and stable these regions are compared to surrounding crust. Seismic waves traveling through the Earth also provide a picture of cratonic roots that extend hundreds of kilometers deep. Together, these lines of evidence support the view that continental seeds formed early and grew into stable blocks over billions of years. Uncertainty remains, however, about exactly when plate tectonics in its modern form began. Some scientists argue that true plate tectonic processes with subduction zones and spreading centers started more than 3 billion years ago. Others propose that the early Earth operated under a different style of tectonics, with smaller crustal fragments moving and interacting in ways not fully comparable to today. What is clear is that continental seeds existed by the early Archean eon, and that their growth required repeated cycles of melting, collision and reworking. The existence of these seeds also hints at the resilience of the Earth's crust. Even in an environment of high heat and constant bombardment, patches of crust could stabilize and endure for billions of years. These survivors carry a record of processes that shaped the planet at a time when its surface was far more dynamic and unstable than today. Each craton that we study represents not only a geological feature, but also a preserved fragment of the Earth's earliest history. By the time continental seeds have established themselves, the stage is set for more complex crustal behavior. Stable blocks exist that can act as anchors for larger continental growth. The balance between creation and destruction continues, but now the Earth holds crust that is not easily erased. This growing stability introduces a long-term memory to the planet's surface. From this point forward, parts of the Earth's crust will persist across eons, carrying records of collisions, mountain-building erosion, and reshaping. The continents as we know them are still far in the future, but the seeds from which they will grow are already firmly in place. Beneath the crust, slow but powerful movements take place in the mantle. This region of the Earth is mostly solid, yet over very long periods of time, it behaves as a viscous material able to flow slowly. The circulation of this material is called mantle convection, and it provides the main driving force for the movement and evolution of the crust above. Mantle convection arises because the interior of the Earth remains hot-heated by residual energy from formation and by the decay of radioactive elements. Hotter, less dense regions of the mantle rise, while cooler, denser regions sink. This continuous motion transfers heat outward from the deep interior toward the surface. The process can be understood step by step. Heat deep in the mantle causes material there to expand slightly, lowering its density. This material begins to rise toward the surface. As it moves upward, it gradually cools. When it loses enough heat, it becomes denser than its surroundings and begins to sink back down. This cycle repeats endlessly with rising plumes of warm mantle rock and descending slabs of cooler material. Although the speed of movement is extremely slow, often only a few centimeters each year, the effect over millions of years is immense. It reshapes the surface by breaking apart crust, pushing it upward, or dragging it downward into the mantle. Mantle convection is not uniform everywhere. In some places, upwelling is concentrated into narrow rising plumes, which can produce hotspots at the surface. In other areas, broader zones of mantle rise beneath spreading centers where new oceanic crust forms. Where cooler, denser lithosphere sinks into the mantle, subduction zones mark descending limbs of the convection cycle. The crust therefore responds directly to what occurs in the mantle, though the connection is complex and varies with location and time. The concept of convection is supported by physical evidence. Laboratory experiments with heated fluids show similar patterns of rising and sinking motion when there is a temperature difference between the bottom and the top. Computer models of Earth's interior also demonstrate that heat flow and density differences can sustain convection over billions of years. Seismic studies that track the speed of waves traveling through the Earth reveal regions where mantle material is hotter and slower, as well as regions where it is colder and faster. These observations confirm that the mantle is not static but actively circulating. One of the key aspects of mantle convection is its relationship with the lithosphere, which includes the crust and the rigid uppermost mantle. The lithosphere is broken into plates, and these plates are carried slowly across the surface by the convective currents below. In this way, mantle convection acts as the engine of plate tectonics. The plates themselves respond by moving apart at spreading centers, colliding at convergent boundaries, and sliding past one another at transform faults. Each of these surface expressions traces back to the slow circulation within the mantle. Mantle convection also influences the thickness of the crust. Where hot material rises, the lithosphere tends to be thinner and more buoyant, often creating elevated regions such as mid-ocean ridges. Where cold material sinks, the lithosphere thickens and subsides, forming deep ocean trenches. These variations in crustal thickness in turn affect the elevation of the Earth's surface and the distribution of oceans and continents. Thus, convection shapes not only the behavior of plates, but also the topography of the planet. The role of mantle convection in early Earth may have differed from the present. When the planet was hotter, overall convection may have been more vigorous with faster circulation and more frequent melting at the surface. Some scientists suggest that during the Archean eon, the style of tectonics was less organized, with smaller fragments of crust being moved around by intense mantle flow. Over time, as the Earth cooled, convection slowed and became more structured, supporting the stable system of large plates that dominates today. This cooling trend continues even now as heat loss gradually reduces the intensity of mantle motion. Another aspect of mantle convection is its influence on magmatism. Rising mantle plumes can melt partially as they ascend, generating magma that may erupt at the surface. This process produces volcanic hotspots, such as those that created the Hawaiian Islands. Similarly, at spreading centers, mantle upwelling generates new oceanic crust. Subduction zones, by contrast, involve descending material that drags water into the mantle, lowering melting temperatures and creating arc volcanism. All of these volcanic processes are linked to convection, showing how deep movements manifest at the surface. Mantle convection also contributes to the recycling of materials. Oceanic crust that forms at spreading centers eventually cools, becomes denser, and sinks back into the mantle at subduction zones. In this way, elements are cycled between the surface and the interior. Some of this recycled material can later rise again in plumes, bringing traces of ancient crust back to the surface. Geochemical analyses of volcanic rocks sometimes reveal evidence of such recycling, showing that parts of the mantle have been influenced by crustal material that returned to depth long ago. While the principles of mantle convection are well understood, many details remain under study. The exact patterns of flow deep within the mantle are difficult to determine. Some models suggest that convection involves the whole mantle from the core to the surface, while others propose that it occurs in separate layers with limited mixing between upper and lower mantle. The balance between large-scale plumes and smaller convective cells is also debated. These questions remain active areas of research, yet the overall role of mantle convection as the engine of crustal change is firmly established. In the present Earth mantle, convection continues at its slow but steady pace, shaping the crust above. It is the underlying force that drives the continuous motion of plates, the opening and closing of oceans, and the building of mountains and trenches. Without it, the crust would be static and unchanging. With it, the crust remains dynamic, always adjusting to the circulation beneath. The crust is thin compared to the mantle, yet it responds to the movements below in ways that create the surface features we observe today. From the earlier stages of Earth's history to the present, mantle convection has remained a central process. It links the deep interior with the outer surface, transferring heat and reshaping the crust. It is not a process that can be seen directly by the human eye, but its influence is visible in every ridge, trench, volcano and continent. Step by step, over immense spans of time, the slow currents of the mantle guide the changes of the Earth's crust, ensuring that the planet's surface is never fixed but always in motion. At the boundaries where plates move apart, new crust forms. These places are called spreading centers, most often found along mid-ocean ridges. Here, mantle material rises to fill the gap created by diverging plates. As it rises, the pressure on it decreases, which allows it to partially melt. The molten rock or magma moves upward and erupts on the seafloor, where it quickly cools to form new basaltic crust. This process repeats continuously, producing a steady supply of fresh oceanic crust that slowly pushes older crust away from the ridge axis. The geometry of a mid-ocean ridge can be described step by step. At its center lies a narrow valley or rift, where the plates are pulling apart. Flanking this rift are ridges of young basaltic rock that form from repeated eruptions. Farther away from the axis, the crust becomes progressively older and thicker. Because the newly formed crust is hot and buoyant, it stands higher than the surrounding seafloor. With time, as it cools and contracts, it subsides and sinks deeper. This creates a distinct pattern of high ridges at the spreading center and lower plains farther away. The evidence for this process comes from several lines of observation. Mapping of the seafloor using sonar has revealed the global network of mid-ocean ridges, which together extend for more than 60,000 kilometers. Magnetic surveys of the ocean floor show symmetrical stripes of magnetized rock on either side of ridges. These stripes record reversals of Earth's magnetic field over time, providing direct proof that new crust is added in a continuous and symmetrical manner. Drilling into the ocean floor has recovered cores of basalt that confirm the age progression. The youngest rocks are at the ridge, while the oldest are found thousands of kilometers away near subduction zones. The chemistry of the magma that forms oceanic crust also provides insight. It is typically low in silica and rich in iron and magnesium, producing dark basaltic rocks. As magma erupts and cools, it forms a layered structure known as an ophiolite sequence. At the top are pillow lavas, which are bulbous structures formed by rapid cooling in water. Beneath these are sheeted dikes, vertical intrusions that fed the lavas. At greater depth lie gabbros, coarse-grained equivalents of basalt. This sequence is repeated across the seafloor and preserved in some ancient mountain belts on land, where pieces of former oceanic crust have been uplifted. Hydrothermal activity is another important feature of spreading centers. Seawater circulates through cracks in the newly formed crust, becoming heated by underlying magma. When it returns to the surface, it discharges as hydrothermal vents, often called black smokers. These vents deposit minerals such as sulfides of iron, copper, and zinc, forming chimney-like structures. They also support unique ecosystems of microorganisms and animals that thrive without sunlight, relying instead on chemical energy. Hydrothermal systems are not only crucial for biology, but also play a role in altering the chemistry of the ocean and modifying the physical properties of the crust itself. The rate at which spreading occurs varies from place to place. Some ridges, such as the Mid-Atlantic Ridge, spread slowly, only a few centimeters each year. Others, like the East Pacific Rise, spread much faster, up to more than 10 centimeters per year. The speed influences the shape of the ridge. Slow-spreading ridges tend to have deep, rugged rift valleys, while fast-spreading ridges are smoother and broader. These differences reflect how magma is supplied and how the crust responds to extension. Spreading centers do not always remain in fixed positions. As plates reorganize, ridges can shift, split, or even become inactive. Over geologic time, entire ocean basins can open and close, with new crust forming at spreading centers and old crust being consumed elsewhere. The Atlantic Ocean, for example, continues to widen today as new crust is added along the Mid-Atlantic Ridge, while the Pacific Ocean is shrinking as its crust is subducted beneath surrounding continents. The process of seafloor spreading also provides a mechanism for recording the history of Earth's magnetic field. As basalt cools, minerals such as magnetite align with the direction of the field at that time. When the field reverses, new crust records the opposite orientation. The alternating stripes of magnetic polarity preserved on the ocean floor act like a tape recorder, preserving a continuous record of reversals over tens of millions of years. This evidence was central to the development of plate tectonic theory in the 20th century, showing that the seafloor itself moves and carries continents along with it. Spreading centers are not limited to oceans. In some cases, continental crust begins to rift apart in a similar process. The East African Rift is a modern example where extension is pulling the continent apart, creating valleys, volcanic activity, and lakes. If the process continues for tens of millions of years, a new ocean basin may eventually form with a spreading center, generating oceanic crust between diverging continental margins. Thus, spreading centers represent a fundamental mode of crustal creation, whether beneath oceans or within rifting continents. From a reflective perspective, spreading centers highlight the balance between destruction and creation in the Earth system. While oceanic crust is constantly formed at ridges, it is also constantly destroyed at subduction zones. No part of the ocean floor is older than about 200 million years, because all older crust has been recycled into the mantle. This contrasts sharply with continental crust, which can persist for billions of years. The oceanic crust is therefore transient, always renewed by the slow but steady process of seafloor spreading. At any given moment, spreading centers mark the places where Earth's surface grows. They are constructive boundaries creating new material and pushing the plates apart. The crust formed here is destined to move away to age and eventually to be consumed, but the cycle of creation remains uninterrupted. The ridge system encircles the planet, a continuous reminder that the Earth's surface is dynamic, shaped by processes deep within. Step by step, ridge by ridge, the crust is renewed, ensuring that the outer shell of the planet is in constant motion and transformation. Opposite in character to spreading centers are subduction zones, where the Earth's crust is destroyed rather than created. At these convergent boundaries, oceanic plates sink back into the mantle, beneath either another oceanic plate or a continental plate. Subduction is the essential counterpart to seafloor spreading, balancing the continuous creation of oceanic crust with its removal. Without it, the planet would be covered in ever-expanding oceans of basalt, but with it, the system remains in equilibrium. The principle is simple, yet profound. Dense, cooled oceanic crust cannot remain indefinitely at the surface, so it descends back into the mantle to be recycled. The process begins as oceanic crust ages and moves away from its spreading center. As it cools, it becomes denser, eventually more dense than the underlying asthenosphere. At a subduction zone, this dense crust bends downward, forming a trench at the surface and plunging into the mantle at an angle. The descending slab carries with it sediments, water, and altered oceanic lithosphere. As it sinks, the slab heats, gradually releasing water into the overlying mantle wedge. This addition of water lowers the melting temperature of mantle rocks, generating magma that rises toward the surface. This is why volcanic arcs chains of volcanoes often parallel subduction zones. The surface expression of subduction is dramatic but systematic. The deepest parts of the ocean are trenches formed where the plate bends downward. The Mariana Trench, more than 11 kilometers deep, is the most famous example. Parallel to trenches are arcs of volcanoes such as the Aleutian Islands, the Andes and the Japanese archipelago. Behind these arcs, the crust may stretch and form back-arc basins, adding further complexity. The entire system reflects the balance of descending plates and rising magmas, each tied to the recycling of crust into the mantle. Seismic activity provides direct evidence of subduction. Earthquakes occur along the interface between the descending slab and the overriding plate. As the slab plunges, it can generate quakes that extend hundreds of kilometers below the surface, defining what is known as a Wadati-Benioff zone. These inclined zones of seismicity mark the path of the descending slab deep into the mantle. No other tectonic setting produces earthquakes at such great depths. They provide a clear three-dimensional view of subduction in action, showing how slabs penetrate the interior. Subduction zones are also major sites of crustal recycling. Oceanic crust that formed at ridges is eventually consumed, returning to the mantle. Some of it may remain in the deep mantle for long spans of time, while other parts may melt and contribute to arc magmatism. Geochemical studies of volcanic rocks from arcs reveal signatures of recycled oceanic crust and sediments, demonstrating that surface material is carried down and later re-emerges as magma. This continuous recycling explains why the ocean floor is geologically young compared to the continents. No oceanic crust older than about 200 million years remains, while continental crust preserves rocks more than 4 billion years old. The density difference between oceanic and continental crust is key to understanding subduction. Oceanic crust is thinner and denser, so when it collides with continental crust, it always sinks beneath it. This produces continental volcanic arcs such as the Andes, where the Nazca Plate subducts beneath South America. When two oceanic plates collide, the older, denser one subducts beneath the younger, producing island arcs such as the Marianas. In both cases, the cycle of descent, melting, and volcanism is maintained. Subduction also has important consequences for the growth of continents. The magmas generated by melting above subduction zones are enriched in silica, compared to the mantle producing andesite and rhyolite as well as basalt. These magmas can solidify into new continental crust or add material to existing continents. Over billions of years, this process has built up much of the continental crust we see today. Subduction is therefore not only a mechanism of destruction, but also of construction feeding the long-term growth of continents. The physical structures created by subduction are varied. Trenches mark the place where plates bend downward. Forearc regions lie between trenches and volcanic arcs, often filled with sediments scraped off the descending slab. Volcanic arcs themselves rise as chains of mountains or islands. Back arc basins may open behind arcs resembling miniature spreading centers. Each of these features can be identified in modern settings, giving geologists detailed insight into how subduction zones function. Ancient examples preserved in mountain belts confirm that subduction has been active for billions of years. Subduction zones also influence global cycles of elements. Carbon, for example, is carried into the mantle, in sediments, and altered crust. Some of this carbon returns to the atmosphere through volcanic eruptions, linking subduction to the long-term carbon cycle and climate regulation. Water is likewise cycled descending with slabs and re-emerging in volcanic gases. These cycles illustrate that subduction is not only a geological process, but also part of the larger Earth system, connecting interior dynamics with surface conditions. The depth to which slabs penetrate remains an active area of study. Seismic tomography, which uses seismic waves to image the interior, shows that some slabs sink all the way to the boundary between the mantle and the core, nearly 3,000 kilometers deep. Others appear to stagnate in the mid-mantle. These differences may influence convection patterns and the long-term evolution of the mantle. They remind us that while the principles of subduction are clear, the details are still being investigated. From a reflective viewpoint, subduction zones embody the balance of Earth's crust. They ensure that the surface does not endlessly expand, but instead remains in dynamic equilibrium. Where spreading centers create subduction zones consume. Together, these opposing processes maintain a constant renewal of the outer shell. Without subduction, plate tectonics as we know it could not operate. With it, the Earth's surface remains ever-changing, shaped by cycles of growth, destruction, and renewal. Seen across deep time, subduction zones are fundamental in shaping continents, oceans, and mountain ranges. They recycle crust, generate volcanic arcs, and drive earthquakes. They link the shallow surface to the deep mantle. They demonstrate how the Earth's crust is never fixed but always in flux. Each descending slab is part of a cycle that has operated for billions of years and will continue for billions more, ensuring that the crust remains a dynamic participant in the planet's long history. When an oceanic plate subducts beneath another plate, the process does not simply end with the descent of cold crust. Above the subduction zone, complex interactions create long chains of volcanoes known as volcanic arcs. These arcs are among the most prominent expressions of crustal change, representing places where mantle material melts to form magma that rises and erupts at the surface. The creation of these arcs involves a combination of melting magma differentiation and crustal thickening processes that both reshape and build up the crust. The sequence begins when the descending slab carries with it water and other volatile components that were locked into minerals at the seafloor. As the slab sinks and heats, these volatiles are released into the overlying mantle wedge. Even small amounts of water have a profound effect, lowering the melting temperature of mantle rock. This generates partial melting, producing magmas that are less dense than surrounding material and therefore rise upward. The chemistry of these melts is distinct from magmas formed at mid-ocean ridges. They contain higher amounts of silica and volatile elements, which makes them more explosive when they reach the surface. At the surface, these magmas build chains of volcanoes that parallel the subduction zone. Where oceanic crust subducts beneath another oceanic plate, the result is an island arc such as the Marianas or the Aleutians. Where oceanic crust subducts beneath continental crust, the result is a continental volcanic arc such as the Andes or the Cascades. In both settings, the crust is thickened not only by the accumulation of erupted lava, but also by the intrusion of magma at depth. Many magmas never reach the surface, solidifying underground to form large bodies of intrusive igneous rock. These intrusions add bulk to the crust, gradually increasing its thickness and contributing to long-term continental growth. The material that makes up volcanic arcs has an intermediate composition compared to the basalt of oceanic crust and the granites of continental interiors. Rocks such as andesite and dacite are common, reflecting partial melting and subsequent differentiation of magmas. Over time, repeated eruptions and intrusions enrich the crust in silica, slowly transforming it from oceanic-like compositions toward continental-like compositions. This is one of the main pathways by which continental crust has grown through Earth's history. Volcanic arcs are also closely tied to the building of mountains. As magmas intrude and solidify, they create batholiths, large bodies of coarse-grained igneous rock. These bodies, combined with the folding and faulting caused by the collision of plates, uplift the crust and form mountain ranges. The Sierra Nevada of California and the Andes of South America both illustrate how volcanic arcs can give rise to extensive mountain systems. Crustal thickening caused by arc magmatism is therefore not limited to the volcanic peaks themselves, but extends across wide regions. Arc systems also create complex feedbacks with erosion and sedimentation. As volcanic mountains rise, they are subjected to weathering and erosion. Rivers carry volcanic sediments to nearby basins where they accumulate, and may later be incorporated back into the crust through burial and metamorphism. This cycle of eruption, erosion, and reburial contributes to the recycling of materials at the surface. In this way, arcs not only build crust upward, but also drive the redistribution of sediments across adjacent landscapes. The evidence for arc formation is preserved both in modern and ancient settings. Today, arcs such as the Andes, the Japanese islands, and the Philippines provide direct examples of active processes. Ancient arcs are preserved in the geological record as belts of volcanic and plutonic rocks that have been sutured to continents during past subduction events. Many of these ancient arcs have been deeply eroded, exposing the roots of magmatic systems where intrusions solidified at depth. These exposures reveal the immense volumes of magma added to the crust over time, far greater than what erupts at the surface. Volcanic arcs also demonstrate the connection between crustal processes and hazards. The same volatile-rich magmas that enrich the crust in silica also tend to erupt explosively. Arc volcanoes such as Mount St. Helens, Mount Fuji, and Krakatoa have produced some of the most powerful eruptions in recorded history. While these events are destructive on human timescales, They are part of the longer-term process of crustal construction. Each eruption adds material, alters landscapes, and contributes to the ongoing cycle of growth and erosion. The chemistry of arc magmas provides further evidence of subduction processes. Elements such as boron, strontium, and lead show distinct isotopic signatures that reveal their origin from subducted sediments and altered oceanic crust. These signatures confirm that volcanic arcs are enriched by recycled materials from the surface, carried down in slabs and returned to the surface in new form. This continuous recycling connects the crustal cycle to the deep mantle, highlighting the dynamic exchange between surface and interior. Volcanic arcs also contribute to long-term stabilization of continents. By repeatedly adding thickened, silica-rich crust arcs, build regions that are more buoyant and resistant to recycling. When arcs collide with existing continents, they can merge, adding new terrains to continental margins. Over billions of years, the accretion of volcanic arcs has been one of the main ways continents have grown outward. Much of North America, for example, consists of ancient arcs that were added through collisions during subduction. Reflection on volcanic arcs underscores how crust is both destroyed and created at convergent boundaries. The descending slab removes oceanic crust, while the melting it induces generates new material that builds continental crust. The balance of these processes ensures that while oceanic crust remains temporary, continental crust grows slowly and persists. The continents we live on today are in large part the accumulated product of countless volcanic arcs that operated over billions of years. Seen in this way, volcanic arcs are not isolated chains of mountains, but part of a larger system of crustal renewal. They highlight the role of subduction in driving volcanism, in thickening crust, and in contributing to the gradual transformation of Earth's surface. They also illustrate how the crust is a participant in a cycle of loss and gain, where destruction at depth fuels construction at the surface. Each arc is a record of this cycle, preserved in rock and landscape, marking the places where Earth's crust is constantly being reshaped from within. Among all the regions of Earth's crust, none are more enduring than cratons. These ancient continental cores are the most stable fragments of lithosphere, surviving for billions of years, while other parts of the crust are recycled. Cratons preserve the earliest records of continental formation, offering a glimpse into processes that operated during the Archean Eon. Their persistence is due to their unique structure and composition, which allow them to resist the constant destruction that affects most of the crust. A craton consists of two main components: a shield, where ancient crystalline rocks are exposed at the surface, and a platform where these rocks are covered by younger sediments. Shields are often made up of gneisses, greenstone belts, and granitic intrusions that formed in the Archean. Platforms record a later history, but beneath both lies a deep keel of lithospheric mantle. This keel is colder, thicker, and less dense than the surrounding mantle. Because it is buoyant and mechanically strong, it protects the overlying crust from being easily recycled at subduction zones. In some cases, these keels extend more than 200 kilometers into the mantle, anchoring the cratons like roots. The stability of cratons is also linked to the composition of their crustal rocks. Many are rich in silica and depleted in iron, making them less dense and more buoyant. This buoyancy helps them ride higher on the mantle compared to surrounding crust. Over time, processes such as partial melting and differentiation removed unstable components, leaving behind chemically stable rocks that are more resistant to breakdown. The combination of chemical and physical properties ensures that once a craton is established, it is difficult to destroy. Evidence for the antiquity of cratons comes from radiometric dating of minerals such as zircon. Some zircons preserved in cratonic rocks date back more than 4 billion years, making them the oldest known materials on Earth. These zircons record cycles of melting and reworking that took place in the earliest crust. In places such as the Canadian Shield, the Pilbara Craton of Australia, and the Kapval Craton of South Africa, rocks more than 3 billion years old remain exposed, demonstrating the remarkable longevity of these regions. Cratons also record the formation of greenstone belts, which are sequences of volcanic and sedimentary rocks that have been metamorphosed. These belts often represent ancient oceanic crust and volcanic arcs that became trapped within continental interiors. They show that processes resembling subduction and arc volcanism were active even in the early Earth. The presence of granitic intrusions alongside these belts indicates that continental crust was being reworked and thickened. Together, these features provide a detailed archive of Archean tectonics. Over geological time, cratons have served as nuclei for continental growth. Volcanic arcs, sedimentary basins, and other terrains have accreted to their margins, expanding continents outward. Because cratons are stable, they act as rigid blocks around which more mobile crustal fragments assemble. This accretion process explains why continents have irregular shapes, with ancient cores surrounded by younger belts of deformed rocks. The interior of North America, for example, is underlain by the Canadian Shield, while its margins consist of younger mountain belts added during later collisions. Cratons are also linked to the formation of valuable mineral deposits. The stability and long history of these regions allowed concentrations of gold, diamonds, nickel, and other resources to develop. Diamonds, for instance, are brought to the surface by volcanic eruptions called kimberlites, which originate in the deep cold keels of cratons. Because these keels extend to great depths, where diamonds can form, they serve as unique environments for such deposits. In this way, the geological stability of cratons has direct consequences for Earth's resources. The survival of cratons across billions of years highlights the contrast between continental and oceanic crust. Oceanic crust is constantly destroyed and renewed, while continental crust, once stabilized, can endure almost indefinitely. This endurance gives the Earth a long-term geological memory preserved in the rocks of cratons. By studying them, scientists reconstruct the early history of the planet, including the onset of plate tectonics, the nature of early crust, and the conditions under which life emerged. Despite their stability, cratons are not completely immune to change. They can be modified by processes such as rifting, magmatic intrusion, or orogeny. In some cases, parts of a craton may be broken apart during supercontinent cycles. However, even when altered, the cores often remain intact, surviving through multiple episodes of continental assembly and breakup. This resilience ensures that cratons remain a central feature of Earth's crustal architecture. Geophysical studies confirm the distinct nature of cratonic roots. Seismic waves travel faster through cratonic lithosphere than through surrounding mantle, indicating that it is colder and more rigid. Studies of mantle xenoliths, fragments of mantle rock brought to the surface by volcanic eruptions, show that cratonic keels are depleted in minerals that would normally make mantle dense. This depletion contributes to their buoyancy. Together, these observations explain why cratons remain stable while other lithosphere is recycled. The importance of cratons extends beyond geology into the environmental conditions of the early Earth. Stable land masses provided environments where weathering could occur over long timescales, releasing nutrients into oceans and influencing the chemistry of the atmosphere. By providing stable surfaces, cratons also created places where early ecosystems could establish and evolve. Their persistence ensured continuity in Earth's surface environments, linking the deep interior with the outermost biosphere. From a reflective viewpoint, cratons represent endurance within a system defined by constant change. They are witnesses to billions of years of Earth's evolution, surviving bombardment, tectonic collisions, and mantle convection. Their presence today allows scientists to read the earliest chapters of Earth's story. They are not simply blocks of ancient rock, but anchors of the continent's keystones in the dynamic balance of crustal creation and destruction. Cratons demonstrate that while much of the crust is temporary, some parts achieve stability that transcends eons. They embody the principle that the crust is shaped not only by rapid processes like volcanism and subduction, but also by the slow accumulation of stability through chemical and physical selection. In the grand narrative of Earth's crust, cratons are the persistent characters enduring through cycles of rifting and collision, standing as reminders of the earliest solid surfaces of our planet. Even though cratons anchor the continents with their stability, not all crust remains fixed. At various times in Earth's history, continents have been stretched and pulled apart, creating rift systems that can eventually lead to the opening of new ocean basins. Rifting occurs when tectonic forces driven by mantle convection act to thin and fracture continental crust. Instead of being compressed and thickened as in collisions, the crust is extended, broken, and subsides. This process not only reshapes continents, but also produces passive margins where continents meet oceans in stable, long-lived boundaries. The initial stages of rifting are marked by the development of faults and fractures. As the lithosphere is pulled apart, it breaks into blocks that tilt and subside, creating elongated valleys known as rift basins. Volcanic activity is common during this stage as the thinning crust allows magma from the mantle to rise through fractures. These early rift valleys often contain lakes, volcanic deposits, and sediments eroded from the uplifted shoulders of the rift. A modern example is the East African Rift, where extension is producing a series of valleys, volcanoes, and lakes across thousands of kilometers. If extension continues, the crust thins to the point where it breaks apart completely. At this stage, upwelling mantle generates basaltic magma that begins to create new oceanic crust. The Rift Valley becomes a linear sea and eventually a full ocean basin. The Red Sea illustrates an intermediate stage where rifting has progressed far enough that oceanic crust is forming between diverging continental margins. If the process continues for millions of years, the Red Sea will widen into an ocean like the Atlantic. Once an ocean basin is fully established, the margins of the continent that border it become passive. A passive margin is a transition from continental crust to oceanic crust, without active subduction or volcanism. These margins are characterized by broad shelves, thick accumulations of sediments, and relative stability. The eastern coast of North America is a passive margin formed when the supercontinent Pangaea rifted apart and the Atlantic Ocean began to open. Today, the Appalachian Mountains stand inland as remnants of an earlier collision, while the coastal plain and continental shelf mark the rifted edge. Sedimentation plays a key role in shaping passive margins. Rivers carry vast quantities of sediment from the continental interior, depositing them on the broad shelves and in deep marine basins at the margin. Over time, these sediments can accumulate to thicknesses of several kilometers, recording the history of erosion and deposition. Passive margins therefore serve as major archives of Earth's environmental history. They also provide important resources including petroleum and natural gas, which are often trapped in sedimentary layers. Rifting does not occur everywhere at once, but tends to localize in zones of weakness. Ancient sutures where continents once collided may later be reactivated as rift zones. Mantle plumes rising from below can also initiate rifting by thinning and heating the lithosphere. The interaction between deep mantle processes and surface forces determines when and where continents begin to split. Once started rifting can proceed for tens of millions of years before a new ocean basin is established. The evidence for past rifting events is preserved in geological records. Ancient rift basins can be identified by their characteristic fault-bounded structures, volcanic rocks, and thick sedimentary sequences. These basins often contain important fossils and climate records showing how rifting influenced ecosystems and environments. For example, The Newark Basin in eastern North America records rifting associated with the opening of the Atlantic, preserving sediments from the Triassic and Jurassic periods. Rifting also affects the thermal structure of the lithosphere. As crust thins, it allows heat from the mantle to rise closer to the surface. This elevated heat flow influences not only volcanism, but also the subsidence of the rift basin. When extension slows or stops, the thinned crust cools and contracts, causing further subsidence. This thermal subsidence explains why passive margins remain low-lying and accumulate thick sequences of sediments long after active rifting has ended. Over Earth's history, repeated cycles of rifting and collision have assembled and broken apart supercontinents. Each cycle begins with rifting that separates land masses and opens new oceans. These oceans widen as seafloor spreading continues, then eventually close again as subduction consumes oceanic crust. In this way, rifting is the first stage in the grand cycle of continental reorganization known as the Wilson cycle. Without rifting, supercontinents would not break apart, and the continual reshaping of Earth's surface would not occur. Modern examples of rifting provide insight into the early stages of this cycle. The East African Rift shows how extension fractures continental crust, producing volcanism and rift valleys. The Red Sea illustrates the transition towards seafloor spreading, with new oceanic crust forming between diverging margins. The Atlantic Ocean represents the mature stage where rifting has long since ceased and passive margins dominate. Each of these settings offers a snapshot of a different phase in the evolution from rift to ocean basin. Rifting also demonstrates the balance between stability and change in the crust. While cratons endure for billions of years, rifting shows how even the most stable land masses can be broken apart under the right conditions. The process is slow operating over tens of millions of years, yet its effects are profound, creating entirely new ocean basins and reshaping continents. The contrast between ancient stable interiors and dynamic rift margins highlights the complexity of crustal evolution. From a reflective perspective, rifting and passive margins show how the crust records both disruption and stability. The scars of ancient rifts remain visible in geological structures long after oceans have opened or closed. Passive margins preserve sediments that document climate, sea level, and life through deep time. These features remind us that the crust not only responds to forces from the mantle, but also preserves the history of those responses etched in valley shelves and sedimentary layers. Thus, rifting and passive margin development represent a vital part of the story of Earth's crust. They show how continents can split, how oceans can be born, and how stable boundaries can emerge from processes of extension. Together with subduction and collision, they ensure that the crust is never static but always engaged in cycles of transformation, balancing stability with renewal across the immensity of geological time. The breaking and spreading of continents through rifting eventually leads to the assembly and breakup of supercontinents, a recurring process in Earth's history known as the Wilson cycle. This cycle describes the opening and closing of ocean basins and the gathering and dispersal of continents across geological time. It is named after the geophysicist John Tuzo Wilson, who recognized that the life of an ocean follows a predictable sequence of birth, growth, and closure. Supercontinents are temporary arrangements lasting hundreds of millions of years before they are torn apart and later reassembled in new configurations. The crust participates in this cycle, repeatedly shaping the geography of the planet. The Wilson cycle begins with rifting within a continent. As extension pulls the crust apart, a new ocean basin opens, creating passive margins on either side. This stage is currently visible in the Atlantic Ocean, which began to open around 200 million years ago, when the supercontinent Pangaea fragmented. As spreading continues, the ocean widens and seafloor spreading dominates its evolution. Passive margins collect sediments, while mid-ocean ridges create new oceanic crust at the center. This represents the mature stage of the cycle, where continents are separated by wide oceans. Eventually, however, the cycle turns toward closure. Subduction zones form along the margins of the ocean, consuming oceanic crust and drawing continents closer together. As subduction progresses, volcanic arcs and mountain belts develop, narrowing the ocean basin. When two continents finally collide, the intervening ocean disappears and a new mountain range is created. The Himalayas are a modern example of this stage, where the Indian plate collides with Eurasia, closing the Tethys Ocean and building the highest mountains on Earth. After collision, the joined landmasses form part of a new supercontinent. Supercontinents influence not only crustal dynamics, but also climate and life. When continents cluster together, weathering, atmospheric circulation, and ocean currents change dramatically. Vast interior regions of supercontinents become arid, while coastlines are limited compared to the global ocean. Life on Earth has repeatedly experienced evolutionary shifts during supercontinent cycles, influenced by environmental changes tied to continental arrangement. Although the Wilson cycle is primarily a geological framework, its consequences extend to every part of the Earth system. The evidence for past supercontinents comes from multiple lines of research. Geological belts show where continents once collided, preserving sutures marked by ophiolites, metamorphic rocks, and mountain roots. Paleomagnetism records the ancient positions of continents relative to the poles, allowing reconstructions of continental drift. Fossil distributions across now separated continents also reveal earlier connections. For example, the presence of the same plant fossils in South America, Africa, India, and Antarctica confirms their union within Gondwana. These diverse sources of evidence support reconstructions of supercontinents across billions of years. Several supercontinents are recognized in Earth's history. The earliest proposed supercontinent is Valbara, which may have formed more than 3 billion years ago. Later, Kenorland assembled around 2.5 billion years ago, followed by Columbia, also known as Nuna, around 1.5 billion years ago. Rodinia formed about 1 billion years ago, and broke apart before 600 million years ago, giving rise to the supercontinent Gondwana and its northern counterpart Laurasia. These eventually merged into Pangaea about 300 million years ago, which later fragmented into the continents we see today. Each of these supercontinents demonstrates the repetitive nature of the Wilson cycle. The processes that drive the Wilson cycle are tied directly to mantle convection. Upwelling beneath continents may initiate rifting, while downwelling slabs pull continents together through subduction. The pattern of convection evolves slowly, but it ensures that continents are never permanently fixed in place. The long-term result is a continuous rearrangement of Earth's surface, a balance between dispersal and assembly. This rearrangement is slow on human timescales, but dominant across geological time. The impact of supercontinent cycles on crustal structure is profound. Collisions during assembly create massive mountain belts, such as the Appalachians, the Urals, and the Himalayas. These belts record the suturing of continents and often remain as stable features long after the supercontinent breaks apart. Rifting during breakup leaves scars that later serve as zones of weakness, often reactivated during future cycles. In this way, the crust carries the memory of each cycle, preserving both the creation of mountains and the stretching of rifts. Supercontinents also stabilize large portions of continental crust by welding together cratons and arcs. The repeated accretion of fragments strengthens continental interiors, making them more resistant to later destruction. Over time, the continents themselves become mosaics of terranes, arcs, and cratons, all assembled through multiple Wilson cycles. North America, for example, is composed of Archean cratons stitched together with younger orogenic belts, many of which formed during supercontinent assembly. The structure of modern continents cannot be understood without considering the repeated cycles of joining and separation. Climate and sea level are likewise influenced by the Wilson cycle. During supercontinent assembly, mountain building increases weathering rates, which can draw down atmospheric carbon dioxide and influence global temperatures. The arrangement of continents controls ocean circulation, which affects climate patterns and the distribution of life. The breakup of supercontinents often coincides with periods of biological diversification, as new shallow seas and coastlines provide habitats. The geological and biological records together highlight the far-reaching consequences of crustal cycles. The Wilson cycle also illustrates how crustal change is both destructive and constructive. Oceans that open and widen eventually close, erasing large areas of oceanic crust. At the same time, continental crust accumulates and persists through collisions. The cycle ensures that while the surface pattern of continents changes, the overall balance of crustal types remains. The continents endure through multiple cycles, carrying with them the evidence of past supercontinents. Modern Earth provides examples of different stages of the Wilson cycle coexisting. The Atlantic Ocean is in the mature stage, widening as seafloor spreads. The Pacific Ocean is in a closing stage, surrounded by subduction zones that consume its crust. The Himalayas represent the final stage of collision, while the East African Rift shows the earlier stage of breakup. Together, these examples demonstrate that the Wilson cycle is not a single sequence occurring everywhere at once, but a global pattern unfolding at different rates in different places. From a reflective perspective, the Wilson cycle emphasizes the cyclic nature of Earth's crustal evolution. Continents are not permanent fixtures, but participants in a long sequence of assembly and breakup. Each supercontinent represents a chapter in this sequence, shaping not only geology, but also the broader Earth system. The crust records these cycles in mountains, rift sutures and basins, preserving the story of repeated renewal. Step by step, the Wilson cycle reminds us that change in Earth's crust is inevitable, guided by processes that operate steadily over immense spans of time. While the Wilson cycle highlights long-term continental movements, other processes reshape the crust on shorter timescales, yet with equally profound consequences. Among these are the formation of large igneous provinces, vast outpourings of magma that flood continents or oceans with enormous volumes of basalt, unlike the steady, narrow eruptions at spreading centers or arcs. Large igneous provinces represent exceptional episodes when mantle melting produces volumes of magma far greater than normal tectonic processes. These events build thick accumulations of volcanic rock, alter the composition of the crust, and sometimes affect climate and life on a planetary scale. The origin of large igneous provinces is usually linked to mantle plumes. A plume begins as a column of unusually hot mantle that rises from deep within the Earth, perhaps as deep as the boundary between core and mantle. When the plume head reaches the lithosphere, it spreads laterally, decompresses and melts extensively. This produces immense quantities of basaltic magma. Instead of erupting through narrow volcanic arcs, the magma floods across wide regions, producing plateaus and provinces of volcanic rock that may cover hundreds of thousands of square kilometers. The Deccan Traps of India and the Siberian Traps of Russia are well-known examples, each consisting of layers upon layers of solidified lava. The scale of these eruptions can be appreciated by considering their thickness and extent. Lava flows may stack to form plateaus more than 2 kilometers thick, extending across regions larger than many countries. The Siberian Traps, for instance, cover an area of about 2 million square kilometers. The volume of magma erupted during such an event can exceed several million cubic kilometers. These outpourings often occur over a few million years, which is short by geological standards. The result is a rapid addition of volcanic material to the crust, dwarfing typical volcanic activity. The composition of magmas in large igneous provinces is mainly basaltic, but they can also include more evolved rocks where magma ponds differentiates and interacts with continental crust. In continental settings, intrusions of magma at depth may trigger melting of the crust, creating granites or rhyolites alongside the basalts. In oceanic settings, flood basalts contribute to the thickening of oceanic plateaus, such as the Ontong Java Plateau in the Pacific Ocean. These features rise above the surrounding seafloor and alter patterns of oceanic circulation and sedimentation. Large igneous provinces have lasting effects on crustal structure. By adding thick volcanic layers, they increase the buoyancy and elevation of the crust. This can influence erosion and drainage patterns for millions of years. The hard basalt layers resist erosion, forming high plateaus or steppe-like landscapes as seen in the Columbia River Basalt Province of the northwestern United States. At depth, the intrusive roots of these provinces contribute to the thickening of continental crust, adding stability over the long term. In this way, large igneous provinces are both transient in their eruptions and permanent in their geological consequences. Beyond geology, the environmental impact of large igneous provinces is significant. The eruption of vast amounts of magma releases gases such as carbon dioxide and sulfur dioxide. These gases can alter climate by warming through greenhouse effects or cooling through the formation of reflective aerosols. The Siberian traps, which erupted about 250 million years ago, coincide with the Permian mass extinction, the most severe biological crisis in Earth's history. While the exact causal links remain debated, many scientists argue that the gases released by these eruptions contributed to global warming, ocean acidification, and widespread ecological collapse. The Deccan traps erupting 66 million years ago overlap with the extinction of the dinosaurs. Although the Chicxulub impact is recognized as the primary trigger, the Deccan eruptions likely compounded the environmental stress. The study of large igneous provinces therefore bridges crustal dynamics with the history of life and climate. They remind us that crustal processes do not operate in isolation, but influence the atmosphere, hydrosphere, and biosphere. Each eruption represents a sudden pulse of mantle energy expressed at the surface, reshaping not only the crust but also the global environment. Geological evidence of ancient large igneous provinces is preserved in thick sequences of basalt, often deeply eroded to reveal their layered structure. Radiometric dating provides ages for these eruptions, linking them to global events in the fossil and sedimentary record. Geochemical analyses of basalts reveal mantle sources and the role of plumes, distinguishing these magmas from those formed at ridges or arcs. Together, these lines of evidence demonstrate that large igneous provinces are a recurring feature of Earth's history, punctuating the otherwise steady rhythm of plate tectonics. Not all mantle plumes produce large igneous provinces. In many cases, plumes form smaller hotspot volcanoes such as Hawaii. The difference may lie in whether the broad head of a plume encounters lithosphere in a way that allows extensive melting. When conditions align, the result is an extraordinary outpouring of basalt that dwarfs normal volcanic systems. These events may be infrequent, but their influence is disproportionate, reshaping the crust and altering Earth's systems on multiple scales. From a reflective perspective, large igneous provinces illustrate how the Earth's crust is subject to both steady and episodic change. Spreading centers and subduction zones represent continuous processes operating predictably over long times. Large igneous provinces, in contrast, are exceptional, occurring rarely, but leaving lasting marks. They remind us that crustal evolution is not uniform but punctuated by extraordinary events. Each province stands as a geological monument to deep mantle dynamics expressed suddenly at the surface. In considering crustal change, large igneous provinces highlight the interaction of deep earth processes with surface environments. They demonstrate how a mantle plume rising from thousands of kilometers below the surface can influence not only the structure of the crust, but also the trajectory of life on the planet. They show that the crust is more than a passive shell. It is an active participant in global systems, recording the rare yet powerful pulses of energy that emerge from the deep interior. Within the crust itself, rocks are continuously altered by heat, pressure, and fluid interaction. This process is called metamorphism, meaning a change in form. Metamorphism does not melt rocks completely, but transforms their minerals and textures while they remain solid. Alongside metamorphism, partial melting and magma differentiation occur, reshaping the composition of the crust from within. Together, these processes recycle existing material, create new magmas, and contribute to the diversity of rock types that make up the continents. Metamorphism begins when rocks are buried to greater depths by tectonic processes. As burial increases, temperature and pressure rise, and minerals that were stable near the surface become unstable. They react to form new minerals that are stable under the new conditions. For example, clay minerals in shale transform into mica minerals in slate when subjected to pressure and heat. With further metamorphism, slate becomes schist, and schist can progress into gneiss. Each step represents reorganization of minerals into more stable arrangements, producing new textures such as foliation, where minerals align into parallel layers under directed pressure. The setting of metamorphism varies. At subduction zones, rocks are dragged deep into the earth, experiencing high pressures but relatively low temperatures. This produces blue schists and eclogites, distinctive rocks that indicate subduction conditions. At continental collisions, rocks are buried and heated, producing regional metamorphism across wide areas. Contact metamorphism occurs where hot magma intrudes cold rock, creating narrow zones of recrystallization around the intrusion. These different settings create a wide range of metamorphic rocks, each recording the specific conditions they experienced. Partial melting often accompanies metamorphism. When rocks are heated beyond certain thresholds, parts of them begin to melt while other parts remain solid. The melt is typically enriched in silica and lighter elements, while the residue is depleted and denser. This process produces magmas that differ from their source rocks. For example, partial melting of basalt can generate andesitic or rhyolitic magmas. These magmas are less dense and rise toward the surface, contributing to the formation of continental crust. The leftover solid material, meanwhile, may become denser and sink deeper into the mantle. Magma differentiation adds another layer of complexity. As magma cools, minerals crystallize in sequence according to their melting points, a process known as fractional crystallization. Early formed minerals are often dense and settle to the bottom of the magma chamber, leaving the remaining liquid enriched in silica. Over time, this can transform a basaltic magma into more evolved compositions such as andesite, dacite, or rhyolite. These lighter magmas build continental crust, contrasting with the denser basalts of oceanic crust. Differentiation therefore explains how the Earth can generate such a wide variety of igneous rocks from relatively simple mantle sources. Evidence for metamorphism and partial melting is visible in ancient mountain belts and continental shields. Exposed metamorphic rocks reveal the mineral assemblages that formed under specific conditions. Index minerals such as garnet kyanite and sillimanite indicate particular ranges of pressure and temperature, allowing geologists to reconstruct the metamorphic history of a region. Migmatites rocks that show both metamorphic and igneous features record partial melting in action, where parts of the rock melted to form veins of granite, while other parts remained solid. These rocks demonstrate the dynamic interplay between solid-state transformation and the creation of new magmas. The role of fluids in metamorphism and melting is also critical. Water and carbon dioxide can infiltrate rocks through fractures and pores, lowering melting points and promoting chemical reactions. In subduction zones, water released from the descending slab triggers melting in the mantle wedge, fueling volcanic arcs. In continental crust, fluids can mobilize elements and redistribute them, concentrating ores such as gold and copper. Metamorphism is therefore not only a process of mineral transformation, but also of chemical transport linking deep earth processes to surface resources. Metamorphism contributes to crustal strength and weakness in complex ways. In some cases, recrystallization produces stronger, more resistant rocks. In others, alignment of minerals into foliation planes creates zones of weakness that influence deformation and faulting. These changes affect how crust responds to tectonic stress, shaping mountain belts, faults, and shear zones. The distribution of metamorphic rocks in orogenic belts provides insight into the forces and depths involved in continental collisions. Partial melting and magma differentiation play central roles in the growth of continental crust. Each episode of melting produces magmas enriched in silica, which rise and solidify as granitic rocks. Over billions of years, repeated cycles of melting and differentiation have gradually enriched the continents in silica and light elements, making them distinct from oceanic crust. This process explains why continents are permanent and buoyant, while oceanic crust is recycled. The crust has thus evolved chemically through a series of selective processes that remove denser components and preserve lighter ones. From a reflective standpoint, metamorphism and melting highlight the continual transformation of crustal material. Rocks that once formed at the surface may later be buried, metamorphosed, and partially melted only to rise again as new magmas. This cycle blurs the distinction between destruction and creation. Nothing in the crust remains static. Every rock carries a history of change, often recorded in its mineral structure. Gneiss may preserve traces of earlier sedimentary or igneous origins, while granite may derive from partial melting of ancient metamorphic rocks. Each rock is a product of repeated cycles of transformation. Modern analytical techniques allow scientists to read these histories in detail. Isotopic dating of minerals reveals when metamorphism occurred, while geochemical analyses show the sources of magmas. Microscopic studies of mineral inclusions record pressure and temperature conditions. Together, these tools reconstruct the deep processes that are otherwise invisible. By studying metamorphism and melting, scientists pieced together the dynamic history of crustal evolution, from mountain building to continental growth. In the grand view of crustal change, metamorphism, partial melting, and differentiation represent the internal transformations that balance the external processes of rifting, subduction, and volcanism. They ensure that the crust is not only moved and reshaped, but also chemically and mineralogically renewed. They demonstrate that the crust is active even at depths far below the surface, constantly reorganizing its materials in response to heat, pressure, and fluids. Step by step, these processes have built the complex and varied crust we observe today, a mosaic of rocks transformed and reworked countless times over geological history. The Earth's crust does not only change through violent collisions, rifting, or melting, it also adjusts quietly and continuously to maintain balance. This principle is called isostasy, the concept that the crust floats on the denser ductile mantle beneath, much like blocks of wood float on water. Where the crust is thick, as in mountain ranges, it sinks deeper into the mantle. Where the crust is thin, as in ocean basins, it rides higher, Over geological time, this floating balance controls the elevation of continents, the depth of ocean basins, and the long-term stability of landscapes. Alongside isostasy, crustal flexure, bending under loads such as ice sheets or volcanic piles, further demonstrates how the crust responds to weight and adjusts to maintain equilibrium. The principle of isostasy can be explained by density differences. Continental crust is thick and composed of lighter silica-rich rocks, so it floats high, forming landmasses above sea level. Oceanic crust is thinner and denser, so it floats lower, creating deep basins filled with water. Within continents, mountain belts formed by collisions represent thickened crust that pushes roots deep into the mantle. The Himalayas, for example, rise high above the surface because their crust extends down as much as 70 kilometers, creating a route that supports their elevation. Without this balance, mountains would collapse under their own weight. Isostatic adjustment occurs whenever mass is added or removed. When glaciers advance, their weight depresses the crust, pushing it deeper into the mantle. When the ice melts, the crust rebounds slowly upward, a process known as post-glacial rebound. This is still happening today in regions such as Scandinavia and Canada, where crust once buried under kilometers of ice is rising several millimeters each year. Similarly, when sediments accumulate in large river deltas or basins, their weight causes subsidence. When erosion removes mountains, the crust rebounds upward to compensate for the lost mass. These adjustments occur over thousands to millions of years, reflecting the ductile response of the mantle to changing loads. Flexure complements isostasy by describing how the lithosphere bends under uneven loads. When volcanic islands such as Hawaii form, the immense weight of lava flows causes the underlying lithosphere to sag, creating a moat-like depression around the island. Sediments often accumulate in these depressions, preserving a record of flexural response. In mountain belts, the weight of growing ranges bends the crust downward at their margins, forming fallen basins. These basins collect sediments eroded from the mountains, linking erosion and deposition directly to crustal flexure. The evidence for isostasy and flexure comes from multiple observations. Measurements of gravity show that mountain ranges and plateaus have less mass beneath them than expected if they were supported only by their visible rocks. This deficit reflects buoyant support from crustal roots. Geodetic surveys reveal uplift in formerly glaciated regions, confirming rebound in response to melting ice. Drilling and seismic studies of basins reveal their flexural origin consistent with models of lithospheric bending. These diverse observations support the view that isostasy and flexure are fundamental principles of crustal behavior. Isostasy also helps explain why continents are long-lived features. Because continental crust is buoyant, it resists being subducted and recycled. Oceanic crust, by contrast, sinks when it becomes dense enough, ensuring its destruction within a few 100 million years. The buoyancy of continents is a direct result of isostasy, and their persistence over billions of years is tied to this principle. Without isostasy, the contrast between continents and oceans would not be as sharp, and Earth's surface would look very different. On shorter timescales, isostatic and flexural adjustments shape landscapes in subtle ways. As erosion lowers, mountains rebound, lift them back up, extending their lifespans. This feedback ensures that mountains can persist for hundreds of millions of years despite constant erosion. In coastal regions, the balance between sediment deposition and subsidence determines whether shorelines advance or retreat. In tectonically quiet regions, isostatic adjustment explains why ancient shields remain elevated, while surrounding basins collect sediments. These quiet processes are less visible than volcanism or earthquakes, but equally important in shaping the surface. Isostasy also interacts with climate. The advance and retreat of ice sheets during ice ages imposed changing loads on the crust. Post-glacial rebound not only raises land but also alters sea levels and stresses in the lithosphere, sometimes triggering earthquakes. In river systems, erosion of highlands and deposition in lowlands create shifting patterns of uplift and subsidence. Thus, climate-driven processes feed back into crustal adjustments, linking surface environments to deep Earth responses. Flexure shows how elastic and ductile properties of the lithosphere influence crustal change. The lithosphere behaves elastically over short timescales, bending without breaking under loads. Over long timescales, it flows ductilely, allowing permanent adjustments. This dual behavior explains why volcanic islands or mountain belts initially produce sharp bending that later smooths out as the mantle flows. It also explains why basins deepen steadily under continuous sediment loading. Flexure provides the mechanical detail that complements the buoyant principle of isostasy. From a reflective perspective, isostasy and flexure remind us that crustal change is not always violent or abrupt. Much of it is quiet adjustment, a slow response to weight and density differences. Mountains, basins, and coastlines are shaped not only by tectonic collisions or rifts, but also by this constant balancing act. The crust, though rigid in appearance, behaves dynamically over time, floating and bending to maintain equilibrium. Each rise and fall of land, each basin that fills with sediments, and each rebound of a glaciated region reflects this underlying principle. These processes also emphasize continuity in crustal evolution. While collisions and rifting come and go, isostatic balance operates constantly, adjusting to whatever changes occur. It is a principle that applies equally to ancient mountains, modern ice sheets, and future landscapes. Step-by-step isostasy and flexure ensure that the crust adapts to its loads, redistributing weight and maintaining balance across geological time. In the grand mosaic of crustal change, they are the steady, quiet forces that keep the surface in equilibrium, complementing the more dramatic forces of tectonics and volcanism. Alongside tectonic and magmatic processes, the crust is continuously shaped from above by erosion, transport, and deposition of sediments. These processes break down rocks, move the resulting fragments, and deposit them in basins where they accumulate into new layers. Over geological time, erosion and sedimentation recycle vast amounts of crustal material, sculpt landscapes, and create new records of Earth's history. While tectonic processes drive the building of mountains and the movement of plates, erosion and sedimentation act as their complement, wearing down elevated regions and filling in low areas, ensuring that the crust remains dynamic even at the surface. Erosion begins with weathering, the breakdown of rock by physical and chemical processes. Physical weathering includes the cracking of rock by freeze-thaw cycles, the expansion of minerals under heat, and the action of plant roots. Chemical weathering alters minerals through reactions with water, oxygen, and acids. Feldspars in granite, for example, can break down into clay minerals under chemical weathering. Together, physical and chemical weathering weaken rock and produce sediments ranging from coarse gravel to fine clay. These sediments are then available for transport by water, wind, or ice. Rivers are the main agents of sediment transport. They collect material from mountain slopes and carry it downstream, gradually wearing away highlands and depositing sediment in valleys, deltas, and continental shelves. The Nile, Mississippi, and Amazon are examples of river systems that carry enormous sediment loads, building deltas that extend coastlines outward. Wind also transports sediments, especially in arid environments where fine sand and dust can be carried across continents. Glaciers act as powerful transporters in cold regions, grinding rock beneath them into fine particles and depositing mixtures of clay, sand, and boulders called till. As sediments are transported, they are sorted by size and density. Rivers deposit coarse gravel and sand near their sources, while finer silt and clay are carried farther before settling in lakes or oceans. This sorting creates distinct sedimentary environments, each with characteristic deposits. Beaches accumulate well-sorted sand deserts, form dunes of wind-blown grains, and deep oceans collect layers of fine clay and the remains of microscopic organisms. Each environment leaves behind a specific sedimentary record that geologists can interpret to reconstruct past landscapes and climates. When sediments reach basins, they accumulate in thick layers that can eventually lithify into sedimentary rocks. Lithification involves compaction, as the weight of overlying layers squeezes sediments together, and cementation as minerals precipitate from groundwater and bind grains. Over millions of years, loose sand becomes sandstone, mud becomes shale, and calcium carbonate shells form limestone. These rocks record not only the materials transported but also the conditions of their deposition, serving as archives of surface processes and environments. Sedimentary basins are closely linked to tectonic processes. Foreland basins form in front of rising mountain belts, collecting sediments eroded from the mountains. Rift basins form as continents stretch and thin, creating space for sediments to accumulate. Passive margins collect thick sequences of sediments from rivers draining continental interiors. Each type of basin reflects the tectonic setting in which it formed, and the sediments they contain record the erosion of surrounding crust. In this way, sedimentation connects surface processes with tectonic events, linking erosion to crustal deformation. Erosion and sedimentation also play a role in isostatic adjustment. As mountains are eroded, their weight decreases, allowing the crust to rebound upward. At the same time, sediments accumulating in basins add weight, causing subsidence. This feedback ensures that highlands and lowlands are maintained with material constantly shifted from one to the other. Over long periods, erosion can strip away entire mountain ranges, exposing deep metamorphic and igneous rocks that once lay kilometers below the surface. These exposures provide direct evidence of crustal processes such as metamorphism and intrusion that are otherwise hidden. The rates of erosion and sedimentation vary widely depending on climate topography and tectonic activity. In regions of rapid uplift such as the Himalayas, erosion is intense, with rivers carrying billions of tons of sediment each year. In stable cratons with low relief, erosion is slow, and sediments accumulate gradually in basins. Climate also exerts a strong influence. Humid regions experience rapid chemical weathering, while arid deserts preserve landscapes with little change. These variations demonstrate that erosion and sedimentation are controlled by both internal tectonic forces and external surface conditions. The record of sedimentary rocks preserves valuable information about Earth's past environments and life. Fossils found in sedimentary layers record the evolution and distribution of organisms. Sedimentary structures such as ripple marks, cross-bedding, and mud cracks reveal conditions of deposition from river channels to tidal flats. Chemical signatures in sediments record changes in ocean chemistry, atmospheric composition, and climate. By studying sedimentary rocks, scientists reconstruct the history of Earth's surface and its interaction with the atmosphere and biosphere. Erosion and sedimentation also play critical roles in the long-term rock cycle. Sedimentary rocks once buried can be metamorphosed or melted to form new igneous rocks. In this way, surface processes feed into deeper crustal cycles. Material is never lost permanently, but is transformed and recycled. Sediments that accumulate in subduction zones may be scraped off and added to continental crust, further illustrating the link between erosion tectonics and crustal growth. From a reflective perspective, erosion and sedimentation show how surface processes complement tectonic processes. while mountain building creates relief erosion wears it down. While rifting and subduction create new crustal structures, sedimentation fills in the basins they form. The balance of uplift and erosion deposition and subsidence ensures that the crust is not static but always adjusting. This quiet but persistent reshaping connects the solid earth with water, air, and life, making sedimentary processes integral to the story of crustal change. Step-by-step erosion removes the highlands, rivers transport sediments, and basins collect the debris. Over time, these layers harden into new rock, recording the passage of landscapes long vanished. In this way, the crust keeps its memory not only in igneous and metamorphic rocks, but also in the layered archives of sedimentary basins. Erosion and sedimentation therefore complete the cycle of crustal change, ensuring that the surface of Earth remains in constant transformation, shaped by forces both deep and shallow, both violent and gentle across the immensity of geological time. To understand how the Earth's crust has changed through time, scientists rely on evidence preserved in rocks and measured through advanced techniques. Paleogeography, paleomagnetism, zircon geochronology, and seismic tomography are among the most important tools for reconstructing the crust's past and present. Each provides a different perspective. Paleogeography maps ancient landscapes. Paleomagnetism records past positions of continents. Zircons preserve the age and conditions of early crust. And seismic tomography reveals the current structure of the crust and mantle. Together, these lines of evidence allow geologists to build a coherent picture of crustal evolution. Paleogeography seeks to reconstruct ancient configurations of continents, oceans, and mountain ranges. It relies on sedimentary records, fossils, and structural evidence to map out how landscapes once appeared. Sedimentary basins preserve evidence of ancient shorelines, river systems, and desert environments. Fossils reveal the distribution of organisms, showing where continents were connected. For example, the presence of identical plant and reptile fossils in both South America and Africa supports their past union in Gondwana. By assembling these pieces of evidence, geologists reconstruct maps of Earth's surface at different times, tracing the movements of continents and the opening and closing of oceans. Paleomagnetism provides another key perspective. As basaltic lava cools, magnetic minerals within it align with Earth's magnetic field. These minerals preserve both the direction and the inclination of the field at the time of cooling. Because Earth's magnetic field is aligned with its rotation axis, the preserved inclination reveals the latitude where the rock formed. By studying magnetic signals in rocks of different ages, scientists reconstruct the past positions of continents. This method was central to confirming the theory of plate tectonics, as magnetic stripes on the seafloor provided direct evidence for seafloor spreading. Paleomagnetic data also allow reconstructions of supercontinent cycles, showing when and where landmasses assembled and dispersed. Zircon geochronology provides insight into the earliest history of the crust. Zircons are durable minerals that survive erosion, metamorphism, and melting, preserving isotopic information for billions of years. Uranium and thorium within zircon decay to lead at known rates, allowing precise dating of the mineral. Some zircons from Western Australia are more than 4 billion years old, providing the oldest direct evidence of continental crust. Isotopic compositions of these zircons also record information about the conditions under which they formed, such as the presence of water. In this way, zircons are time capsules that preserve details of the early Earth long after other rocks have been destroyed. Seismic tomography provides a modern view of the crust and mantle by using seismic waves generated by earthquakes. As waves travel through the Earth, their speed depends on the temperature, composition, and density of the materials they pass through. By measuring arrival times at seismic stations around the world, Scientists construct three-dimensional images of the interior. These images reveal subducting slabs descending into the mantle, plumes rising from deep sources, and variations in crustal thickness. Tomography shows, for example, that some slabs sink all the way to the core mantle boundary, while others stagnate at mid-mantle depths. It also reveals the deep keels of cratons, confirming their stability. These methods are not independent but complement one another. Paleogeography reconstructs surface environments, while paleomagnetism provides quantitative data on continental positions. Zircons supply absolute ages, anchoring reconstructions in time. Seismic tomography shows present structures, helping interpret how past processes continue to influence the mantle. Together, these approaches allow geologists to link events across different scales, from the crystallization of a mineral grain to the assembly of supercontinents. The application of these techniques has transformed our understanding of Earth's crust. In the 20th century, paleomagnetism provided the decisive evidence for plate tectonics, overturning earlier views of fixed continents. Zircon geochronology has revealed that continental crust formed much earlier than once believed, with stable fragments appearing in the Hadean. Seismic tomography continues to refine models of mantle convection, showing how deep structures influence surface tectonics. Each advance demonstrates the value of combining multiple lines of evidence. Paleogeographic reconstructions also help explain patterns of climate and life. The distribution of deserts, glaciers, and shallow seas in the past is tied to continental positions. The breakup of Pangaea, for example, created new coastlines and shallow marine habitats that influenced the diversification of life in the Mesozoic. Paleomagnetism confirms the latitudinal positions of these environments, while sedimentary records show their specific conditions. By combining these sources, scientists link crustal movements with global environmental change. Zircons extend this record into the earliest times when no complete rocks survive. Their isotopic signatures indicate the presence of liquid water more than 4 billion years ago, suggesting that Earth's surface cooled quickly after its violent formation. This has profound implications for understanding the origin of life and the early stability of the crust. Without zircons, knowledge of this ancient period would be extremely limited, as nearly all other rocks from that time have been destroyed or reworked. Seismic tomography, though focused on the present, provides context for how the crust evolved. Imaging of subduction zones shows that slabs can remain coherent as they descend, recycling oceanic crust into the mantle. Imaging of mantle plumes explains the origin of hotspots and large igneous provinces. Imaging of continental roots demonstrates why cratons endure. Each feature connects deep mantle dynamics with surface geology, showing that the crust is part of a broader system extending to the planet's core. From a reflective perspective, these methods highlight the interplay between evidence and theory. The crust itself holds records in rocks and minerals, while modern instruments extend our view into the deep earth. Each discovery builds upon multiple lines of evidence, confirming the processes that drive crustal change. The strength of our understanding lies not in a single observation, but in the convergence of many, all pointing to the dynamic nature of the crust. Together, paleogeography, paleomagnetism, zircon, geochronology, and seismic tomography demonstrate that the crust is not only an active participant in geological processes, but also a faithful recorder of them. The continents we walk upon, the rocks we study, and the seismic waves that pass through the Earth all carry information about past and present. By reading these records carefully, scientists reconstruct the story of how the crust has evolved, linking surface landscapes to deep mantle circulation and tracing cycles of creation and destruction across billions of years. Today, the Earth's crust is a mosaic of different structures that reflect the long history of creation, destruction, and renewal. It is divided into two main types: the oceanic crust, which is dense, thin, and relatively young, and the continental crust, which is thick, buoyant, and ancient. Together, these crustal types cover the surface, constantly reshaped by tectonic processes driven by the mantle below. The present-day arrangement of ridges, trenches, cratons, mountain belts, and passive margins is the cumulative result of billions of years of change. Oceanic crust dominates the floor of the oceans. It forms at spreading centers where mantle material rises, melts, and solidifies into basalt. From there it moves outward, cooling and becoming denser with age until it eventually subducts at trenches. Because it is recycled so efficiently, no oceanic crust older than about 200 million years exists. The Pacific Ocean, for example, contains vast stretches of oceanic crust actively descending beneath surrounding arcs. The Atlantic Ocean, in contrast, is younger and still widening at the mid-Atlantic ridge. The cycle of formation and destruction ensures that oceanic crust remains youthful on a geological scale, constantly renewed, yet never permanent. Continental crust presents a stark contrast. It is older, thicker, and chemically distinct, enriched in silica and light elements. Much of it is made up of granitic rocks that are buoyant and resistant to recycling. The oldest known pieces of continental crust preserved in cratons such as the Canadian Shield and the Pilbara Craton of Australia are more than 3 billion years old. These ancient cores are surrounded by younger belts of deformed rocks that record successive collisions, rifts, and magmatic intrusions. Unlike the transient oceanic crust, continental crust represents a long-term archive of Earth's geological history, preserving rocks from almost every stage of evolution. The boundaries between oceanic and continental crust are marked by active and passive margins. At active margins, such as the west coast of South America, subduction zones generate volcanoes, earthquakes, and mountain building. At passive margins, such as the eastern coast of North America, thick sediments accumulate quietly on wide shelves and slopes. These margins record both the tectonic and surface processes that shape the crust, from violent collisions to gradual sedimentation. They illustrate how the crust is not uniform but varied, reflecting the diverse conditions under which it formed and evolved. Mountain ranges represent another key feature of today's crust. They form at convergent boundaries where plates collide, thickening the crust and producing elevated terrains. The Himalayas, rising from the collision of India and Eurasia, are still growing as convergence continues. The Alps, Andes, and Rockies each tell their own stories of past and present collisions. Within these mountains, metamorphic and igneous rocks are exposed, revealing the deep processes of crustal transformation. As mountains rise, erosion wears them down, transporting sediments to adjacent basins, which in turn record the cycle of uplift and erosion. Mountains are therefore both builders and sources, shaping crustal structure and sedimentary archives simultaneously. Volcanic arcs and hotspot volcanoes add to the mosaic. Arcs trace the boundaries of subduction zones, forming chains such as the Andes and the Japanese islands. Hotspot volcanoes such as Hawaii represent mantle plumes rising independently of plate boundaries. Together they add new material to the crust, contributing to its chemical diversity. Large igneous provinces, though rare, have left behind plateaus and traps that remain distinctive in the geological record. These volcanic features demonstrate how mantle processes imprint themselves on the crust, in different ways from steady arcs to massive outpourings. Sedimentary basins complete the picture by recording surface processes. Foreland basins in front of mountain ranges rift, basins in zones of extension and passive margin, basins along stable coasts all preserve thick sequences of sediments. These basins contain records of past environments, climates, and life. They show how erosion redistributes material from highlands to lowlands, balancing uplift with deposition. In doing so, they link the surface to deeper tectonic forces demonstrating how crustal deformation and sedimentation are inseparable. The present crust also shows the scars of past events. Ancient suture zones mark where continents once collided. Rift valleys reveal where crust has stretched but not yet broken apart completely. Exposed shields show the roots of ancient continents that have survived multiple cycles of assembly and breakup. Each feature is a layer in the story of crustal evolution, preserved in rock and structure. Modern tools provide detailed views of this crustal mosaic. Satellite measurements reveal motions of a few centimeters per year, showing how plates shift across the globe. Seismic imaging displays the thickness of crust beneath mountains and basins. Geochemical analyses of rocks trace their origins to specific tectonic settings. These methods confirm that the crust is dynamic, always moving, thickening, thinning, and recycling. What may appear stable at human scales is revealed to be active at geological scales. The present-day crust is also shaped by interactions with climate and life. Glaciers carve valleys, rivers cut canyons, and coral reefs build limestone platforms. Human activity now adds to these processes, altering erosion rates, redirecting rivers, and extracting resources from sedimentary, igneous, and metamorphic rocks alike. While small compared to tectonic forces, these activities demonstrate the close connection between crust and biosphere. The crust provides the foundation for ecosystems, climate regulation, and human civilization, while life and climate influence the crust in return. From a reflective standpoint, the current state of the crust represents a balance between persistence and change. Cratons endure as ancient anchors while oceanic crust cycles rapidly. Mountains rise and erode, basins fill and subside, ridges spread, and trenches consume. The crust is a patchwork not uniform but varied, recording every kind of process, from the deepest subduction to the quietest sedimentation. At any moment, the crust embodies both ancient stability and ongoing transformation, linking the earliest history of the planet with the continuous dynamics of the present. The modern mosaic of the crust is therefore not an endpoint but a moment in an ongoing sequence. Each ridge, trench, craton and basin is part of a cycle that will continue into the future. Continents will drift, oceans will open and close, mountains will rise and erode, and new volcanic provinces will form. The present configuration is simply the latest arrangement in a history that has unfolded for billions of years and will continue for billions more. The crust today, with its varied structures and records, offers a snapshot of this continuous transformation, showing us how Earth's surface embodies the interplay of construction, destruction, and renewal across deep time.